Okay, hello again. So now I want to talk about two other topics on these gravity waves. First one, I want to talk about breaking waves, and then we will talk about waves in a moving fluid. And after that, in the next lecture, I'm going to talk entirely about hydraulic jumps that occur in open channel flows. Okay. So first, let's talk about breaking waves. So imagine you have a gravity ripple or a gravity wave like this that is moving in a fluid in an open channel flow. We have H1 here, H2 here. The velocity at the downstream, is 0. And then we have the drift velocity, delta V, at the upstream of this gravity wave. Okay. So in this scenario, back of the wave it kind of, just look at somewhere here, around here, okay? Back of the wave has a velocity equals to delta V, the drift velocity, plus square root of gh1, which is greater than the velocity at the front of the wave. The front of the wave, I mean somewhere here, okay? Which is square root of gh2, right? So what happens? So what happens is that we have this velocity at the back of the wave is higher, so eventually it comes a little bit from the back towards the front of the wave. So we will see something like this happens. It comes a little bit forward, right? And then finally, this wave breaks. This wave breaks because the back of the wave has a higher velocity from the front of it. So let me just make it a little bit larger. So what happens is that here, because the back has a larger velocity, it comes faster to the front. And what happens is that this generates something like this. So we have here something like this, and then it suddenly starts breaking. It breaks down. This is something that you also see in waves over the ocean, right? The waves break. This is a similar phenomenon, okay? So we have the back of the wave that moves toward the front, and then this wave, because of this difference in the velocity, breaks down. So this is more clear and obvious for waves that are in beaches. So say we have coast, and then we have water here, and also a wave that is generated, and this wave is moving towards the beach. So this difference in the altitudes is larger right? So we will see this more clearly here. So more obvious in beaches. We have these breaking waves because H1 is greater than H2, so C1 plus delta V, which is the drift velocity, is greater than C2. The wave in the back and in the front are different. The velocity, speed of them are different. So we see that these breaking waves occur in beaches. Okay, so this is what one of the reasons, primary reasons we have for these waves that break. Okay, so now I want to talk about waves in a moving fluid. So far we have talked about the waves in a stationary framework, but what if the wave or the water, what if the water also ahead of the wave is moving? So the water ahead of the wave is moving with speed v. The wave is moving at a speed c equals to square root of gy relative to the moving fluid. Okay. So let's see what happens in this scenario. First, I want to talk about I want to talk about circular waves, when we have this kind of circular ripples, let's say, and see what happens when we have them. Okay, so let me see if I can draw circles here. So in a stationary framework where the fluid is not moving, if you keep, say, dripping a sponge into a water at some points with a specific frequency, this is what you see. This is the ripples that kind of propagate, for example, along a lake or something like that. Okay, so these propagate, and the distance here, for example, up to this one, you can get it by calculating square root of, it's going to be a square root of gy and times delta t, right? This is the distance. Okay, so in this scenario, the fluid is not moving, so the speed of the fluid is 0. Okay, and we can also talk about Froude number. So Froude number, which is defined as the speed of the fluid itself over a square root of gy, which is the speed of the gravity wave. This is the definition of Froude number. In this case, Froude number is gonna be what? Because v is 0, it's going to be 0, right? Okay, let's look at the second scenario. So in the second scenario, the velocity of the fluid is not 0. So the fluid itself is also moving. Okay, so the water ahead of the wave is moving with speed c. So this is like you are making these disturbances in a river that is flowing. It's not like a lake. So the left one is like you are making this, for example, disturbances in a lake. For example, in a lake, okay? But on the right one, we are making these disturbances in a fluid that is moving, like in a river. We want to know what happens to these as it is moving, right? So the river, so the first one, say you created it here, and then the second one, because the river is moving to the right, say, okay, so it was created here, but now because the river is moving to the right, so this has to also move to the right a little bit. Okay, the same thing for the oldest one. So this is the oldest one, the oldest disturbances that we made. So we created it here, but because the river is moving, the fluid is moving, so it had to move something like this. Okay. So here, this is the center of the first one. The center of the center of the first one is here, and then the center of the second wave is going to be somewhere here. And this distance, again, let me just copy this one, is this distance is again square root of gy. Okay, so this is the center of the second one. Okay, and this distance, so the river is moving with a v which is not 0, and so this distance is gonna be what? It's gonna be v times delta t. Okay, because the river is also moving to the right. So in this scenario, what is Froude number? Froude number is v over square root of gy, but in this scenario, Froude number is smaller than 1. Why? Because here you see Froude number is what? Froude number is v over square root of gy. So you see this v over square root of gy is smaller than 1, right? Just divide the distance, gray one over the red one. So this is smaller than 1. So this is gonna be, Froude number is smaller than 1. Okay, so here we also call this a subcritical flow. Subcritical, okay, because v is Froude number is smaller than 1. Okay, So this is like you are making disturbances in a river that is moving to the right. Okay. And just before going forward with the other scenarios, I want to mention something, a similarity between Froude number and Mach number. So Mach number, which is mostly in aerospace, is similarly defined as velocity of the fluid over c, which is speed of sound, which is shown as gamma RT, where T is just temperature. Okay, so this is speed of sound. So in this scenario, Mach number is going to be 0, but here, similarly, Mach number is smaller than 1. So instead of like a gravity wave, if you imagine this was a sound wave, we are talking about Mach number. Like this is called a subsonic kind of condition. Okay. So I just wanted to talk about this analogy, and now let's talk about the other situation that might happen. So we might have this type of flow. So if we increase the velocity of the river, so at first it was here, so if we keep increasing the velocity, it's more than this one, it's more than this case. Say the velocity of the velocity is greater than this one. So what's going to happen? So it was up to here at delta t, it's going to go to reach here. Okay. The same thing for this one. So it's going to it's going to go faster and reach here. And so on and so forth we have for larger ones and older waves. We have something like this, okay? So this is a scenario where v equals to square root of gy, right? So these both equal to each other. And so this scenario is where we have Froude number equals to 1 or Mach number equals to 1. So this is a critical flow. Or sonic flow in kind of aerospace literature. Okay, so one interesting thing here is, you see, because of this type of because the velocity of the fluid is equals to the square root of gy. So what happens is whatever wave or disturbances that you create in this scenario, it will reach to a limit like here, right? So we will reach to a limit here. And whatever disturbances you make, so let me show, maybe this one is better. So whatever you make, it will not go to the left of this line, right? Because of this situation we have. So if you have a point here, this point in the flow here does not feel disturbances, all these disturbances. So the flow that is there never feels these disturbances. That is because of this specific situation that occurs here. Okay. We can have one more situation, and that is we can still keep increasing the velocity of the fluid. So what happens then? So first it was here, this is Froude number smaller than 1, this is Froude number equals to 1. And then if you keep increasing that, this will even pass the original one that we had. So it will go somewhere here. And the last one is similar to that. So this one is going to even pass further. It will go somewhere here. So let me put them here. So what actually is happening, we can draw two lines here to show this phenomena better. One is up to here. The second one is something like this, and then we have this one. Okay. Okay, so this is to center of the last one. Yeah, approximately something like this. We can define it like it. And here, the angle is going to be theta. And again, I can show that this, for example, occurs after sometime like square root of gy delta t. And then this line is the length of this line. I can show, maybe let me change the color of it to, is v times delta t. Okay, this is the velocity of the fluid as it moves to the right. So in this scenario, you can clearly see that v is greater than square root of gy. So the Froude number is going to be greater than 1. So this is what we call supercritical flow. Supercritical flow. Or similarly, it's Mach greater than 1, which we call it supersonic flow. And interestingly, again here, this point, the points here, never feel the disturbances. So there is no disturbance here. Or if this was like we're talking about sound waves, is kind of silent here. They are not gonna hear anything. People who are there, any observer there, is never gonna hear anything. So here I can say that sine theta is what? If this is the perpendicular to this, so sine theta is gonna be a square root of gy delta t over v delta t. So these two are gonna cancel out. So what I'm gonna get is square root of gy over v, which is what? Which is actually 1 over Froude number, which we call it Froude angle. Okay. So I want to also bring one more further analogy for this case. This is an analogy that you might have. It's kind of makes maybe kind of you can make this analogy and you are familiar with that. So for cases where we have Froude smaller than 1 and also Mach smaller than 1, this phenomena is like the Doppler effect. I think you have most likely have heard about this effect, the Doppler effect, that explains why the sound of a car or train moving toward you has a higher pitch, or higher frequency than when it is moving away from you, which has a lower frequency or lower pitch. So let's see how. So here we talked about the fluid that is moving to the right. But another way to think about it is as say, let me copy it so we can better talk about it here. Another way to talk about it or understand it is like a Doppler effect. So instead of saying that the fluid is going to the right, we can say, for example, we have, say, a train or a car that is moving toward you. So you are here. Say you are here as an observer. And so this is moving toward you. So first, at the beginning, it makes something like this noise, okay? So it was here. Originally it was here, like it was like a train or like a car, something like this, we can assume. And then it created this kind of noise here, okay? And then it starts moving, so let me make it a little bit larger. It starts moving toward you, and then it will make another noise as it moves forward. So it will make another noise here. And so I can show it, let's say, with this one. So originally it was there, and now it's here. So it's making another noise. So I can change the color of it a little bit. So maybe make it this. Okay. And then again it moves forward, and then it makes a noise here. So let me just remove the color, make it just black. Okay. So what happens is when you are here, what you hear when you are here in this part, you hear a higher frequency of the noise, right? So you can see the wavelength here is smaller. But as this comes and moves over you, so when you are here, it's going away from you, the wavelengths of these things that reach to you become larger, right? So that's why you have this difference in the sound that you are kind of hearing. So when it's moving away, you have a lower frequency wave, but when it is coming toward you, you have a higher frequency sound or higher pitch. And this is known as the Doppler effect, okay? So here in this scenario, the disturbance itself was moving, but not the fluid. But in our cases, the fluid is moving and we keep disturbing the flow at the same place. So it's kind of an analogy to that, so you better understand what we were talking about, okay? So let me review what we talked about this session and this lecture. So we talked about open channel flows. There are flows where there is a free surface between the liquid and gas. We talked about gravity waves. We used a moving CV, a moving framework, to find the speed of the gravity wave, which are small amplitude gravity waves. We use continuity equation and Bernoulli equation along the surface and we got this equation for from the momentum from the Bernoulli equation, and after combining them, we got this relation for the speed of the gravity wave, which is going to be square root of gy, small amplitude ones. And then we talked about breaking waves, circular ripples, and when the waves break. And finally, we discussed waves in a moving fluid framework. So when we have these moving fluids, we will have this type of different frameworks where we can have Froude number equals 0, a subcritical flow where Froude number is smaller than 1, critical flow where Froude number is 1, and a supercritical flow where Froude number is greater than 1. And then I just mentioned an analogy between this phenomena and the Doppler effect that we have in reality. Okay, so in the next lecture, I'm going to talk about hydraulic jumps, which are one type of breaking waves. And we are going to drive the relation for hydraulic jumps, and also discussing flow through a smooth constriction in open channel flows. Thank you very much, everyone.